Hi, this is Ms. Basin, and in this section we're going to talk about concentration of solutions, which is section 4.5. So when we talk about the term concentration, what that means is it describes how much solute is dissolved in a certain amount of solvent or solution. So the term that we use most often to describe concentration is molarity. So molarity, like we've talked about before, is moles of solute per liter of solution. So however many moles of the substance that you're dissolving divided by however many liters of the solution that you're dividing it or that you're dissolving it in. So the easiest way to do these is to look at a couple example problems here. So our first one is calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. So like we said, to calculate molarity, we need moles per liter, or moles divided by liter. So I know I have 23.4 grams of sodium sulfate, which is Na2SO4. So the first thing I have to do is convert that to moles using molar mass. So the molar mass, if I take 2 sodiums plus a sulfur plus 4 oxygens, I get 142 grams. So that gives me 0.165 moles. And then I'm going to take that and divide that by 125 milliliters of solution, which is the same as 0.125 liters. So I just did that milliliters to liters conversion. I moved the decimal over. So and it has to be in liters for this to work. So 0.165 moles per 0.125 liters. So that gives me a final molarity of 1.32. And the unit for molarity is capital M. Okay, another example, calculate the molarity of a solution made by dissolving 5 grams of glucose, so 5 grams of C6H12O6 in water to form exactly 100 milliliters of solution. So just like before, I'm going to convert this to moles. So the molar mass of glucose is 180 grams. And again, molar mass, I'm just adding up 6 C's, 12 H's, 6 O's. So that gives me 0.0278 moles of glucose. To get the molarity, again, I take moles divided by liters. I have 1,000 milliliters, which is 0.1 liter of solution. So that gives me a molarity of 0.278. And again, don't forget the unit. We're going to use capital M for molarity. Okay, the next thing we can look at is you can express the concentration of an electrolyte solution. And we talked about this a little bit at the very beginning, but just to kind of review a little bit, when you have an ionic compound and it dissolves, the concentration of the ions depends on the chemical formula and the original concentration. So for example, for a 1 molar solution of NaCl, it would be 1 molar Na plus and 1 molar Cl minus. So to do that, you figure out what this dissociates into. So this dissociates into Na plus, Cl minus, and it's 1-to-1 ratio here. So you have 1 molar Na plus, 1 molar Cl minus. Now for Na2SO4, when this dissociates, I get 2 Nas, 2 Na plus because of that 2 right there, plus SO4 minus 2. So when I'm looking at the concentration of that, because there's 2 Na pluses, that means it's 2 times whatever that concentration is. So that gives me 2 molar Na plus, and then 1 molar SO4 minus 2, because there's only one of those per whole compound. Okay, so another example problem, or 2 more example problems here. What are the molar concentrations of each of the ions if we have a 0.025 molar aqueous solution of calcium nitrate? So calcium nitrate is CaNO3 2. So when that dissociates, I get Ca plus 2 NO3 minus. Okay, so that means if it's 0.25 molar, then I have 1 calcium, so it's 0.025 molar Ca plus 2, and then I have 2 times that, so 0.05 molar NO3 minus. Okay, so then my next example is potassium carbonate. So if I have a 0.015 molar solution of potassium carbonate, I have K2CO3. So when that dissociates, I get 2K plus, again because of that 2 there, plus CO3 minus 2. So to find my concentration of K plus, I take 2, so let's work it out this way to show what we're doing here. I take 2 times 0.015, so that gives me 0.030 molar K plus. For CO3 minus 2, there's only one of those, so it's 0.015. So it's 0.015 molar CO3 minus 2. Okay, this also allows us to interconvert. Now that we know the formula, we can interconvert between molarity, moles, and volume. And again, we've done this a little bit already with the stoichiometry problems that we started with. But as we go through these, when we look at the molarity, like we've said before, we know that molarity is moles per liter. Okay, so if we know big M equals MOL, or moles per liter. So there's 3 pieces to this. So if we know any 2 of those, we can solve for the third. So a couple example problems with this one. It says, how many grams of sodium sulfate are required to make 0.35 liters of a 0.5 molar sodium sulfate solution? I'm going to go ahead and put both those up there. Okay, so 2 different ways you could look at this. You could say, okay, so I know molarity equals moles over liters. I have liters, I have my molarity, so I could plug those in and solve for moles, kind of like an algebra problem. So I could say I have 0.5 molar, little moles is what I'm looking for, because I have to have moles to get to grams, per 0.350 liters. Okay, so if I solve for that, my moles ends up being Okay, so for my moles, if I solve for moles, I end up with 0.175 moles. Then from that, you would have to do, actually I'm going to do this up here so we can see a little better, 0.175 moles, and then convert it to grams using molar mass. So I have sodium sulfate, so this is the same one I used on that previous one. So I know that 1 mole of sodium sulfate is 142 grams. So that gives me 24.9 grams in that sample. Okay, so that's one way to do it, where you set it up and solve algebraically and then convert it to grams using, again, molar mass. The other way you could do it is you could do it as one long dimensional analysis problem. So in this case, we would start with our volume. So I have 15 milliliters. Convert that to liters. Then use my molarity, since I know that is moles per liter, I can say 0.50 mole, 0.5 moles, and then from there continue on and just do my molar mass calculation here. So 1 mole is still sodium sulfate here, 142 grams. So then that would give me 1.1 grams of sodium sulfate. Okay, the last thing we can do with concentration of solution is something called a dilution. So when you do a dilution, you're taking something that's concentrated and you're diluting it to make something less concentrated. So this formula is also very simple. So it's M1V1, so the original molarity times the original volume equals the new molarity times the new volume. Other ways you may see this is sometimes they'll use dilute and concentrated as the subscripts. There's other various forms of this, but the one we're going to use is M1V1 equals M2V2. And again, the big M stands for molarity, the V stands for volume. So let's look at just a couple examples of these. So this first one says how many milliliters of 3 molar sulfuric acid are required to make 450 milliliters of 1.1 molar sulfuric acid. Now in this case, it's okay to use milliliters, so we can leave it in milliliters as long as the 2 on both sides are the same. It doesn't matter whether you're in liters or milliliters. So we have 3 molar, so I'm going to, just to keep these straight here, I'm going to say my molarity is 3 molar. That's my original. I want to know how many milliliters that I need to make a new or diluted concentration of 0.10 molar. And my new volume is 450 milliliters. So M1V1 equals M2V2. So original molarity is 3. Volume is what I'm solving for. My new molarity is 0.1. and I have 450 milliliters. So my volume here, again I'm going to go up here, is 15 milliliters. So again, original molarity, original volume equals new molarity, new volume. So really with these you just have to make sure you keep the concentrated versus the dilute separate, and you make sure that the volumes and the molarities are together with the right ones. Okay, let's try another one. This one, how many milliliters of 5 molar potassium dichromate? So molarity is 5 molar. We want to know the volume of that one. Has to be diluted to prepare a new volume of 250 milliliters of a new molarity of 0.1. Okay, so same deal here. M1V1 equals M2V2. M1 is 5. V1 I'm solving for. M2 is 0.1. V2 is 250 milliliters. So my V1 in this case is 5 milliliters. So basically what that means is I need to have 5 milliliters of this 5 molar solution, add it to enough water to make 250 milliliters, and that'll give me a 0.1 molar solution.